Consider a uniform magnetic field of strength B. Let a charged particle of charge q be projected into the magnetic field with the velocity v perpendicular to the direction of the magnetic field. When the charged particle is moving perpendicular to the magnetic field, the charged particle experiences maximum force, and this force is acting perpendicular to both the magnetic field and velocity of the charged particle. The magnitude of the force acting on the particle F is equal to BQV sin theta, where theta is the angle between the direction of the velocity and the direction of the magnetic field. Since, in this case, theta is equal to 90 degrees, sin 90 is 1, and hence the force is denoted by F is equal to BQV. We know that when an external force acting on a body is perpendicular to the motion of the body, the work done on the body is said to be zero. In other words, in the expression for work done, W is equal to Fs cos theta. If theta is equal to 90 degrees, we get W is equal to 0. In the case of a charged particle in a magnetic field, the magnetic force is acting perpendicular to the direction of velocity, and thus the work done on the charged particle is 0. As the work done on the charged particle is 0, there is no change in the kinetic energy of the charged particle, and the magnitude of the velocity of the charged particle remains constant. As the magnetic force acting on the charged particle is perpendicular to both the direction of its velocity and magnetic field, the charged particle moves in a circular path, and the magnetic force acts as a centripetal force. Thus, the centripetal force F is equal to BQV. By definition, the centripetal force is denoted by mv square by r, where m is the mass of the charged particle, v is its velocity, and r is the radius of its circular path. Equating these expressions, we get the radius of the circular path, r, is equal to mv by bq. Let this be equation 1. When the momentum mv of the particle increases, the radius of its circular path also increases accordingly, as b and q are constant. Hence, the radius of the circular path of the charged particle moving in an external uniform magnetic field is directly proportionate to the momentum of the charged particle. The charged particle executes uniform motion with a fixed time period t and angular frequency omega. Here, omega is equal to v by r. Let this be equation 2. Comparing equations 1 and 2, the angular frequency of the charged particle omega is equal to bq by m. Let this be equation 3. As you know, the time taken to complete one revolution is called the time period of revolution. Time period t is equal to 2 pi by omega. Substituting equation 3, we get t is equal to 2 pi m by bq. From the expression, it is clear that the time period of revolution of the charged particle is independent of its speed. The reciprocal of time period is called frequency. That is, F is equal to 1 by t. Substituting t in the expression, we get F is equal to BQ by 2 pi m. This frequency is called cyclotron frequency. Cyclotron is a particle accelerator, which we will discuss in another module. Now, consider that the charged particle is projected at an angle theta to the uniform magnetic field, which is anything other than 90 degrees. In this case, we need to resolve the velocity into two components. One component parallel to the magnetic field, Vp, and the other component perpendicular or normal to the magnetic field, Vn. Since Vp is parallel to the direction of the magnetic field, we have Vp is equal to V cos theta. As Vn is perpendicular to the direction of the magnetic field, we have Vn is equal to V sin theta. The component of velocity, Vp, along the magnetic field remains the same because the angle between the parallel component of velocity and the direction of the magnetic field is zero, and hence there is no force acting along the magnetic field. The charged particle moves along the magnetic field due to the parallel component of velocity, Vp. At the same time, due to the normal component of velocity Vn, the charged particle moves in the circular path with radius r equal to m into Vn by bq. Thus, the charged particle has a velocity in the direction of the magnetic field and also in a circular path, whose plane is perpendicular to the direction of the field. Due to this, the resultant path of the charged particle is a helix. The radius of the circular path during the helical motion is called radius of the helix. Here, the axis of the helix is along the magnetic field. The distance moved by the particle along the magnetic field during one rotation in the helix is called pitch. Pitch P is equal to the product of a parallel component of velocity and the time taken to complete one revolution, which is time period of revolution. Substituting t is equal to 2 pi m by bq in the expression, we get P is equal to Vp into 2 pi m by bq, which is equal to 2 pi mv cos theta by bq. So far we discussed the motion of a charged particle in a uniform external magnetic field. What happens if the magnetic field is non-uniform, as in the case of the Earth's magnetic field? In the case of a non-uniform magnetic field, the field lines are not straight. In this case, the helix of the moving charged particle also follows the direction of the curved magnetic field lines. During a solar flare, that is, when a sudden, rapid and intense variation in the brightness of sunlight occurs, a large number of charged particles are ejected from the sun. When these charged particles enter the Earth's atmosphere, they get trapped in the Earth's magnetic field and move in helical paths along the field lines. But near the Earth's magnetic poles, these lines of force come closer to each other. The density of magnetic lines of force increases and the density of charges moving in the helical paths along the magnetic field lines also increases. When the density of the charge increases at the poles, these particles collide with each other and also with the molecules of atmospheric gases. Then the atoms of the atmospheric gases get excited. These excited atoms emit light during de-excitation. Excited oxygen atoms emit a green light during de-excitation. Excited nitrogen atoms emit a pink light during de-excitation. This phenomenon, when it occurs in regions of the North Pole, is called aurora borealis. It is called aurora australis when it occurs in regions of the South Pole. As you learned earlier, charges at rest produce an electric field. Moving charges or a current passing through a conductor produces both an electric and a magnetic field around it. A magnetic field is a vector quantity. It is denoted as B, and when we represent it vectorially, we display it in bold type. The properties of a magnetic field are identical to those of an electric field. Similar to an electric field, a magnetic field also obeys the principle of superposition. Consider B1, B2, and B3 as magnetic fields at a point shown due to three different sources, such as three current-carrying conductors. Then, the resultant magnetic field B at the point is the vector sum of the individual magnetic fields. That is, B is equal to B1 plus B2 plus B3. Now let us learn about the forces acting on a moving charge in the presence of both an electric field and a magnetic field, which is called Lorentz force. Consider a charge of Q coulomb placed in a uniform electric field of strength E. Here, the force acting on the charge due to the electric field is F electric is equal to QE. Consider another charge of Q coulomb moving with the velocity of V in the magnetic field B. Here, the force acting on the moving charge due to the magnetic field is F magnetic is equal to Q into V cross B. The force F is perpendicular to the plane containing the velocity vector and the magnetic field vector. Now, consider a charge of Q coulomb moving with the velocity V in the presence of both electric fields E and the magnetic field B. The net force on charge Q is F, called Lorentz force, acting on the charge and is equal to the vector sum of the forces due to the electric field and magnetic fields. Thus, Lorentz force F is equal to F electric plus F magnetic. That is, F is equal to QE plus Q into V cross B, which can be written as F is equal to Q into E plus V cross B. Now, let us discuss in detail the interaction of a moving charge with the magnetic field. As you know, the force experienced by a moving charge due to the magnetic field is F magnetic is equal to Q into V cross B. As V cross B is equal to VB sin theta, the magnetic force on charge F magnetic is equal to QVB sin theta, where the angle between the directions of V and B is equal to theta. When theta is 0 degrees or 180 degrees, that is, when charge q moves parallel or anti-parallel, respectively, to the magnetic field, we have sin theta is equal to 0. If the charge is moving perpendicular to the direction of magnetic field, theta is equal to 90 degrees. In this case, the charge experiences maximum magnetic force, F magnetic, equal to QVB. If the charge is not moving in the magnetic field, that is, its velocity is 0, then the charge does not experience any force, since F magnetic is equal to 0. When the charge in the magnetic field experiences maximum force, the force is expressed as magnetic force is equal to BQV, which can be written as B is equal to F by QV. The magnetic field strength, B, can be defined as force per unit charge when the charge is moving perpendicular to the magnetic field with the velocity of 1 meter per second. The SI unit of magnetic field is Newton per ampere meter, which is referred to as Tesla. Gauss is another common unit. 1 Tesla is equal to 1 Newton per ampere meter. 1 Tesla is also equal to 10 to the power 4 Gauss. Now let us discuss magnetic force acting on a current-carrying conductor. Consider a conductor of length L with uniform cross-section A and the number of free electrons per unit volume as N. These electrons are moving with an average drift velocity v. Then, the total number of free electrons in the rod is equal to N times the volume of the rod, which is equal to N into AL. The total charge on the rod is equal to the total number of electrons multiplied by the charge on an electron. That is, Q is equal to NAL multiplied by minus E, where minus E is the charge on an electron. This conducting rod is placed in a magnetic field of strength B. As you learnt earlier, for a charge of Q coulomb moving with a velocity v, in the magnetic field B, the force acting on the moving charge due to the magnetic field is F magnetic is equal to Q into V cross B. In the case of the rod, the magnetic force acting on the free electrons is equal to the total charge due to the free electrons on the rod multiplied by V cross B, which is equal to minus NALE into V cross B. As current density J is defined as the current per unit area, it is equal to current I divided by area A, which is equal to minus NEV, where minus E is the charge on the electron and V is the average drift velocity. In this case, the magnetic force can be written as F is equal to AL multiplied by J cross B, since J is equal to minus NEV. From the definition of current density, current I is equal to J multiplied by A. Then, the magnetic force F is equal to I multiplied by L cross B, which can be written as F is equal to BIL sin theta. The Biot-Savart law expresses the relationship between current and the magnetic field produced by the current. The Biot-Savart law is used to calculate the magnetic induction at a point in the magnetic field produced by the current. Now, consider a finite, long conductor, XY, of any arbitrary shape carrying a current I. Let P be a point in the magnetic field of the current-carrying conductor. To determine the magnetic induction B at point P, due to the current carrying, let us assume the conductor is divided into a number of infinitesimally small elements, each of length dl. First, let us calculate the magnetic induction dB at point P, due to one such element of the current-carrying conductor. Then, to obtain the magnetic induction due to all the elements of the conductor, we calculate the sum of the magnetic inductions due to all the elements at point P. Consider one such element of the conductor. Let R denote the vector joining the current element to point P. Let theta be the angle between the tangent to the element in the direction of the current, which is actually the direction of vector dl and vector r. The magnetic induction dB at point P due to the element is directly proportional to the current I in the element. Let this be equation 1. The magnetic induction dB is directly proportional to the length dl of the small element of the conductor. Let this be equation 2. The magnetic induction dB is inversely proportional to the square of the distance r between the element and the point. Let this be equation 3. Combining equations 1, 2, and 3, we get dB proportional to I dl by r square. If we express it in vector notation, we get the magnetic induction dB proportional to I dl Let this be equation 4. Since the magnitude of the cross product dl cross r can be written as dl into r sin theta, we can write equation 4 as dB proportional to I dl into r sin theta by r cube. Let this be equation 5. Replacing the proportionality sign with a constant, we get dB is equal to mu naught by 4 pi into I dl into r sin theta by r cube, which can be written as mu naught by 4 pi into I dl into sin theta by r square. In this expression, mu naught is the constant known as permeability of free space, and the value of mu naught in SI units is equal to 4 pi into 10 power minus 7 Tesla meter per ampere. Here, the direction of B will be perpendicular to the plane containing dl and r, and can be obtained by using the right-hand rule. According to the right-hand screw rule, if we place our stretched palm along the direction of dl, and we now curl our fingers in the direction of vector r, the thumb of the right hand held perpendicular to the stretched palm gives the direction of the magnetic induction dB at point P. The magnetic induction B is obtained by integral dB in suitable limits. Magnetic induction at point P is B equal to integral dB. Now, let us compare the Biot-Savart law with Coulomb's law. Coulomb's law gives the electric field due to a charge at a distance r from the charge, where the source of the electric field is the charge. The Biot-Savart law gives the magnetic field due to current passing through a conductor, where the source of the magnetic field is the current passing through the conductor. According to Coulomb's law, the electric field due to a charge is inversely proportional to the square of the distance between the charge and point P. On the other hand, according to Biot-Savart law, the magnetic field due to an infinitesimal element of the current-carrying conductor is inversely proportional to the square of the distance between the element of the conductor and point P. According to Coulomb's law, the electric field at point P acts along the displacement vector joining the charge and point P. That is, the electric field acts along the line joining the charge and point P. But, according to Biot-Savart law, the magnetic field at point P acts perpendicular to the plane containing vectors dl and r. The magnetic induction at any point P in the magnetic field of the current-carrying conductor depends on the angle between vectors dl and r, whereas there is no such angular dependence in the case of the electric field strength due to a point charge. However, if point P is in the direction of the length of the conductor, the angle between the current and the line joining the point is zero, and hence the magnetic induction dB for such a point due to the current-carrying conductor is zero. The superposition principle is applicable in both cases. For the electric field produced by a system of charges, the net electric field strength E is equal to the vectorial sum of the electric fields E1, E2, E3, and so on due to the individual charges, say Q1, Q2, Q3, and so on by the superposition principle. If a region has more than one current-carrying conductor, then the net magnetic induction B at any point P in the combined magnetic field of the conductors is equal to the vectorial sum of the magnetic inductions. Say B1, B2, B3, and so on, due to each of the conductors. In fact, the speed of light c in a vacuum is related to the permeability of free space μ0, which is related to the magnetic field and permittivity of free space ε0, which is related to the electric field as c square is equal to 1 by μ0 ε0. Consider a region in which a uniform magnetic field of magnetic induction B and uniform electric field of strength E exist. Let a particle with charge q move in this region with a velocity v perpendicular to both electric and magnetic fields. Here, the electric field, magnetic field, and the velocity of the charged particle are mutually perpendicular to each other. When the charged particle moves in both electric and magnetic fields as shown, the particle experiences Lorentz force F, which is the sum of forces due to electric field F electric and the force due to magnetic field F magnetic. Thus, the total force experienced by the charged particle F is equal to Q into E plus V cross B. If the magnitudes of electric field strength and magnetic field strength are adjusted such that the magnitudes of the two forces are equal, then the net force acting on the charged particle is zero. The magnitude of the force on the charged particle due to the electric field is QE, and the magnitude of the force due to the magnetic field is BQV. If the net force on the charged particle is zero, then E is equal to BV or V is equal to E by B. This principle is used to select the particles to be projected into the fields based on their velocity. So the crossed electric field and the magnetic fields are called velocity selectors. The particles, whose magnitude of velocity is equal to the ratio of E to B, pass through the combination of electric field and magnetic field without deviation, and the remaining particles whose velocity is not equal to the ratio of E to B deviate on either side of the electric field. This principle is used in the mass spectrometer and particle accelerators. The mass spectrometer is a device used to separate charged particles based on their charge to mass ratio. Particle accelerators are used to accelerate particles to very high energy. Now we will learn about a particle accelerator, which is also known as a cyclotron. The cyclotron was invented by E. O. Lorentz and his student M. S. Livingston. Let us understand how a charged particle is accelerated in a cyclotron with the help of this model. The cyclotron consists of two hollow, flat, semicircular metal disc-like containers called D1 and D2, as their shapes are similar to the letter D. These two Ds are separated by a narrow parallel gap. These two Ds are connected to a high-frequency oscillator which produces an alternating voltage. This alternating voltage establishes an alternating electric field between the two Ds, once from D1 to D2 and then from D2 to D1. This electric field between the Ds accelerates the charged particle when it passes through the gap between the Ds. Consider a source S placed at the center of the two Ds, which supplies the positive ions to be accelerated in the cyclotron. These Ds are placed in a vacuum chamber to minimize collision with air molecules and ions. This chamber is placed horizontally between two huge magnets, which provide a vertical magnetic field. Inside the Ds, the charged particle is affected only due to the magnetic field. The positively charged particles emitted from the source at the center move in one of the Ds, say D1, in a semicircular path and arrive in the gap between the Ds in time equal to half the time period of the revolution of the particle. We know that the particle revolves with a frequency also known as cyclotron frequency, expressed as Fc is equal to Qb by 2 pi m, where Q is the charge on the particle, m its mass, and B is the strength of the magnetic field. Hence, the time period of the particle will be equal to 1 by Fc, which will be equal to 2 pi m by Qb. When a charged particle enters a D, it moves in a circular path with constant speed because inside the D, it is influenced only by the magnetic field. Inside the D, the electric field is zero due to the shielding effect. The applied AC frequency is adjusted equal to the frequency of the charged particle, so that when the particle just about arrives on the edge of D1, D2 will be at lower potential and the particle is accelerated across the Ds to gain kinetic energy equal to QV, where V is the potential difference across the Ds at that instant of time. The situation or condition in which the frequency of the applied voltage is equal to the cyclotron frequency is called resonance. We observe this as the kinetic energy of the particle increases. Thus, the radius of the circular path increases and the particle now moves in a circular path of greater radius. Inside the Ds, the particle once again travels in a circular path free of the electric field. And every time it crosses the Ds, it gains kinetic energy equal to QV. In this way, the kinetic energy of the particle increases with time and hence the radius of its circular path also increases accordingly till the radius is nearly equal to that of the radius of the D. Then, it is deflected away from the path by the magnetic field towards an exit slit. Thus, on the whole, the path of the charged particle is spiral. The radius of the trajectory r is equal to m into v divided by b into q. The kinetic energy of the charged particle before leaving the system is half mv square is equal to b square q square r square by 2m. The important operation of the cyclotron is that cyclotron frequency is independent of the speed of the charged particle and radius of the circular path. Thus, cyclotrons are used to bombard nuclei with energetic particles by accelerating them and to study nuclear reactions.